So let's see the geometry used for capacitance coupling calculation. The calculation is beyond the scope of the syllabus. I'll just write the formula. But then here is my interconnect 1, here is my interconnect 2. This is the width of my interconnect, this is the spacing between the two interconnects, this is the thickness of my interconnect, and this is the thickness of my oxide layer. And if you stretch this beyond in 3D, you will get the length of your interconnect as well. The reason why we are seeing this geometry is this is going to be very important for us when we understand interconnect scaling. And right now, you have to just remember the coupling capacitance value is given by epsilon 0.03 width of my interconnect upon the thickness oxide plus 0.83 into thickness of my interconnect upon thickness of my oxide minus 0.07 into thickness of my interconnect upon thickness of my oxide. The whole is 0.022, and this entire term is multiplied by S, which is the spacing, upon the thickness oxide raised to minus 1.34. Again, as I mentioned, the derivation is beyond the scope of this course. This is the value of the coupling capacitance, and we can find the total coupling capacitance Cc. This is coupling capacitance per unit length, okay? So we can find the total capacitance Cc by writing this small cc into Lc, because this was coupling capacitance per unit length, which clearly tells us that the length is the length of the coupled section with spacing S. So as I mentioned, this is a 3D, right? This is the length of my interconnect L. It goes in 3D. And the equation shows to us that Cc increases as 1 by S times 4 by 3. You can easily make out this is the spacing factor, this is the coupling capacitance per unit length, and this is the coupling capacitance. If you see all this 3, we can easily make out that the coupling capacitance increase as we keep on reducing the spacing between the two interconnects. We'll see this as we go ahead and do interconnect scaling as well, but this is just the rough idea what we can make out from the equation. Now, if there are two wires, we have already seen that, let's say this is line 1 or interconnect 1 or wire 1, and this is line 2, interconnect 2 or wire 2. We know that the capacitance present on line 1 would be equal to its self capacitance, which is nothing but C11, plus the coupling capacitance, which is Cc. Similarly, for line 2, we can say that it has its self capacitance, which is C22, plus the coupling capacitance Cc. Remember this because this will help us in the derivation when we assume that there are 3 lines or 3 interconnects and we want to see the effect of the change in voltage on one of them on the other 2 lines which are closely placed to it. So here on the screen, I've just done a pictorial representation where this is line 1, this is line 2, and these are the coupling capacitance. I've replaced the interconnect lines with the pi model of RC, which you can see here, correct? This is nothing but a pi model of RC. Same for line 2, and this is the coupling capacitance. Now we want to identify what's going to happen when there's a 3-line network where line 1 is my actual line, and the change in the voltage on that line 1, what amount of change it does on line 2 and line 3. Let's quickly see that. So let's find the charge on line 1. Q1 is equal to, we know that Q is equal to CV, right? So its own capacitance, line 1's capacitance, into the voltage of its own. So say this line has a voltage of V1, this line has a voltage of V3, this line has a voltage of V2. So line 1 has its voltage of V1 and its self-capacitance is nothing but C11. However, it is connected with a mutual capacitance or coupling capacitance to line 2 and line 3 as well. So we already saw that we need to take that into consideration as well, correct? So that is nothing but, let's take first line 2. So line 2 mutual capacitance, we'll call it as from line 1 to line 2, so C12, and change in the voltage or difference in the voltage between line 1 and line 2, which is given by V1 minus V2, plus it also affects line 3. So let's write the capacitance value of line 3 with regards to line 1, so that is nothing but C13, and the voltage change of line 3 with regards to line 1, so that is V1 minus V3. Let's call this as equation 1. Similarly, we can find for Q2 as well. So Q2 is line 2, it has no connection with line 3 if you see the diagram, so this term will not be present. It also has its own capacitance, which is nothing but the self capacitance of line 2, which will be C22, and its own voltage, which is V2, correct? And it is also getting affected by line 1, correct? So So let's call the capacitance from line 2 to line 1 as C21, and the change of voltage or the difference in voltage between line 2 and line 1, because we are considering line 2 right now, so it's going to be V2 minus V1. Similarly, we can write for Q3 as well. Now see, line 3 is not getting affected by line 2 at all. So this term is going to be 0 or not present, correct? Here in this case, this term was 0. Line 3 has its own self-capacitance, which we'll call as C33, into the voltage of its own, which is nothing but V3, and it gets affected by line 1. So line 3 voltage with regards to line 1, or the capacitance between the two, will be given by the line which we are taking into consideration to the line where the voltage change has happened, so C31, into the line which is into consideration, the difference of that line voltage minus the voltage of the line which has induced crosstalk, in simple words, which is V1, so V3 minus V1. So if you see, what I've done is, in simple words, I've assumed the coupling capacitance from lines 1 to 2 and 1 to 3 as C12 and C13. Vi is the voltage on the ith line where I is equal to 1, 2, 3, and I've just written the values of charges.